तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we talked about logic functions and truth tables and how it can be implemented using gates. We took a simple example of a function f, which is, if I remember, was a or b not and not c. That means we said there is a digital system or a circuit, we call it whatever, with three inputs a, b, c, and output f, and this output f is true for this condition of the input combinations, which is output is true if a are true or if b is true and c is not true. And we were able to realize this using gates, an AND gate to get b and not c, an inverter to get not c out of c, and an OR gate to combine a and this term. And we were not sure though whether this was the simplest possible. We just took an arbitrary gate structure and wrote the logic function, and we also said this is true under these conditions, which could be a control for a particular operation in a different situation. And then we wrote the truth table with a, b, c as the input variables and the output f, and we defined certain things like min terms, sum of products, and so forth. So many times we are given either given a function, before you implement it as a logic circuit with gates, or given a logic circuit and you analyze the behavior, we are not sure whether that is the simplest possible circuit in terms of gates, in terms of number of gates and number of inputs of each of these gates, to realize the same function. If I am able to get a same function implemented using a smaller number of gates or with smaller number of inputs for a given gate, I would prefer that because there is a saving in hardware. So there has to be some methods of finding out whether what we have is the simplest possible realization, If not, what are the techniques we can use to reduce the given function or a given circuit to a simpler form? As I said the other day, there are two approaches. One is called Boolean algebra, the mathematical tool wherein you write the function and use some identities and apply these identities to this function, to the left hand side and the right hand side, and simplify it to the extent possible. But the problem with such an approach is we never know which is the minimum possible, whether we reach a minimum, because an identity may not strike you. Somebody else may think of something which you may not be able to think of. You can never be sure of whether a particular minimization reduction is the simplest. The other approach is a graphical method where there is a systematic technique applied to a given function till we reach a specific minimization beyond which you cannot go. But of course, this graphical function is not any different technique. It is only a Boolean algebra, sort of integrated mechanized or automatic procedure. So you automate the procedure so that you will not make a mistake. So it is not that graphical method is called map method. We will see that. It is not that it is totally different technique compared to Boolean algebra. Boolean algebra is the algebra based on the identity, the logical behavior of these variables under different combinations. And the same thing will be applied in a systematic way in a graphical sense, using a map, so that some sort of a tool to go systematically into the function and simplify it to the extent possible. And that is more, what shall I say, that is more practical, easier to implement, and more than that, once you want to do a program or automatic way of reduction using some computer programs, such a technique which is step based technique, automatic procedural based technique, becomes easier to implement as a program so that you can get the best possible results. Because what we are seeing in the class are simple circuits with 2 inputs, 3 inputs, 4 inputs, maximum maybe 4 or 5 inputs, not beyond that, because we cannot handle a circuit like that in a classroom in a given time, in a given space. Also become extremely complex, then the principle or the concept which you are trying to teach you gets submerged in numbers and equations and variables. That is why we always take simple examples. But then in practice, in reality, when you talk of digital systems, as I said, a digital system could be a microprocessor, a computer, or as I said, a traffic control, or as I said, aircraft navigation system, or a missile launch system. Think of those systems, how many variables, how many conditions will be there, and how can you do a simplification if you do not have a systematic procedure to do that. That is why we go for the second method. But before we go to second method, the first method I want to introduce, because it is the basis on which the second method is built. It is a mathematical method. Being a scientific basis on which reduction is based, you should know. So I will briefly introduce Boolean algebra and not use it very much for many reasons, as I said the other day again. Today the reduction at gate level has become more or less not essential, because gone are the days where we need to save gates because of the technology, availability of gates and the availability of circuits in which a lot of these functions can be put in a very simple, small IC. So there is need for reduction at the gate level, which is not as great as it used to be. Even then it is required, because occasionally there are situations where you want to reduce the given function to a fewer number of gates for many reasons. So that is one reason. Second thing is we are going to use the other method, which is going to be more practical method, extensively in the course. For that reason also you don't have to learn Boolean algebra very much, but still, as I said, I want to introduce this concept. So let us again take the same example, this given system, digital circuit which we wanted to implement. If you remember, there are 3 inputs, and the three inputs can have 8 different combinations. And for these combinations, the output is true. That means if A is true, the output is true. Or if B is true and C not true, B is true and C not true. B is true, C not true, but already this is true because of A is 1. So for the rest of the combinations, the output is 0. This is the truth table, we called it. And I also mentioned this, each of these row is called a min term, wherein all the inputs are present either in the true form or the complement form. And you can write a function which is true form as a sum of products. That means this is a sum of products. That means we have an output which is written as a series with terms which are AND functions. And when you say product, you give a mathematical analogy, arithmetic analogy. When B and C, even though it's B and not C, call it a product, B, C, not. When you read it, you say B, C bar, so it's a product. And even though this is an OR function, we call it a sum because it's a plus sign. So this is a sum of product. When you write it from the truth table, we get what is known as a canonical sum of product. I said that. So we'll first write the canonical sum of products. And the canonical sum of products will have the min terms corresponding to each of the term, each of the input combinations for which the output is true. So when you write that, that becomes a canonical sum of products. So each of these product terms is called a min term. So F is true if A is not true, B is true, C is not true, right? If it's true, A is not true, B is true, not C not true, then A is true, and all possible combinations. A is true, B not true, C not true, A true, B not true, C true, etc., etc., all the 4 combinations. So A true, B not true, C not true, A true, B not true, C true, A true, B true, C not true, A true, B true, C true. These are the 5 combinations of inputs, true or not true, for which the output is true. The other combinations are the combinations for which the output is false. If you write it in this form, this is a canonical sum of products because it has all the possible combinations for which the input combinations for which the output is true is expressed in this form. And this, as I said, is also called, why is called sum of products, because it looks like a product term combined by a sum series. Even though it's AND and OR functions were operations we are referring to, AND is loosely referred to as a product operation and OR is loosely referred to as a sum operation. And each of these terms is called a min term. There are 8 min terms in this, out of which for 5 min terms the output is true, for 3 other min terms output is false. So we write this sum as, this sum function as sum of all the min terms for which the output is defined as true. Is that clear? Now let me show you how to apply the Boolean algebra to this to get this form. Simplified form. So let us use now Boolean algebra. What is a Boolean algebra? After all, it's a very simple thing. See, now we can, it's a logical, again, fortunately for us, it's not a very complex mathematics because there are only, each variable can only take 2 values, A and A bar. So it's a binary operation. So the binary operation, the functions can be very easily understood, even though there may be a rigorous mathematical proof for some of these identities and theorems, as we call it in Boolean algebra. From a understanding point of view, it is only simply a 2 level. You can always verify it by simply giving 2 different values for each of these things and verifying whether it is true or false. If you make a statement, you can quickly say whether it is true or false by giving values for all the functions, all the variables in their function, and each of these function variables can only have 2 values. So give all the possible values and verify it for all possible input combinations, and the output is true. So I can verify this without any formula or mathematics by simply giving alternately 0, 1, 0, 1 for A, B, C, and then for each one of them whether true or false, and then we verified. So what are the simple rules we are going to use? I am not going to introduce Boolean algebra in a rigorous sense, as I said it is not required. Just to give you a idea, flavor of this, so that you should not think this is all some heuristic procedures which may or may not work under different conditions. I don't want you to go with that impression. That's why I am just introducing this to you as a concept, as I said, even though it is not important. So what are simple identities? Supposing I have 2 functions, I have a function and it has 2 values, so OR combination of A or A bar. That means I have A, in other words I have an OR gate in which 2 inputs are connected, one as the function A, the other is the complement of that function. The output has to be 1, because if one of them is true, the output is true. If A is true, A bar is false. If A is false, A bar is true. If one of them is going to be true, it is going to be true. So this is first of the Boolean identities, if you want to call it that. We will only be using such simplification procedures here, that is all, not great things. Similarly, I can have an OR combination of 2 variable and its complement. The output has to be 0, because in AND combination, when both the inputs are true, only then the output can be true. So I am giving the variable and its complement as inputs. If one of them has to be necessarily false, so the output has to be necessarily false. Most of the time this itself will do for reducing our Boolean expressions, because when you have a redundant term, a term with A and a term with A bar with a common variable, we can take the common variable out and put A plus A bar, knock it off as 1. Similarly, we may have this, A and A bar, knock it off as 0. Most of the time that is good enough. For example, if we have a function A, what I mean by this is, suppose I have A or AB. So that means I have a gate with AB as input, feed into a this is not, this is A and B, this is A or A and B. Now let us use the Boolean algebra. A or AB what is 1 or B? Because 1 is an input which is always true, and in an OR function, if one of the inputs is true, the output has to be true. So 1 or B has to be 1. So I can knock it off and say as 1. So A or 1, A and 1. A and 1 is A, because if A is true, function is true. If A is false, the function is false. So this is A. That means A or AB is A, because of the fact 1 or A is 1, 1 and A is A. This also can be, you want to list them all as identities. This is one of them, identity. This is another identity. This is another identity. This is another identity. This is another identity. That means if I have a variable present in 2 terms and with one without an extra term, with extra term, then there is no need for this extra term. That means this OR gate is redundant, this AND gate is redundant, as if its transmission is A. A is true, this function is true. A is false, this function is false. If you are not convinced, you can always verify it by giving, as I said, a truth table. I can draw A, B, AB. So it is 0, 0. Oh, I'll write it here. I said A or AB is A. So I already showed that can be done by using this relationship. 1 or B is 1, A and 1 is A. But then if you are not convinced, you always write a truth table, AB, AB, A or AB, 0, 0, 0, 1, 1, 0, 1, 1, AB 0, 0, 0, 1 because AND gate, correct? And A or AB is this or this, which is 0, this or this is 0, 1, 1. So this is same as this is one other way of proving Boolean algebra or Boolean identities, any Boolean identities. But what I have not mentioned here is all this formula, all these properties of commutation, distribution and all that you are applying to normal algebra. For example, A and B is same as B and A. A or B is same as B or A. So it's called commutative law. Distributive, A or A and B or C same as AB or AC. It's a distributive law. All these simple rules of algebra we use can be used here. For example, I use this here. So laws of commutation, distribution and all those things are applied here also equally well. As I said, I am not going to rigorous Boolean algebra treatment. That's why I just left out those which are all very simple things, which are the things but of which we are very familiar. I am just skipping so that we can get the essence of this. So what I am saying is by repeated application of these things, whenever you find a term like this, you can knock it off and get it. Say, yeah, so you can think of this as simplification. Think of this as simplification. Correct? Two other identities and then we will stop this. For example, we have, suppose we have A what do you think this will be? A or not A and B. A or not A and B. So you can just write this if you want to. A, B, this is 0 because B is 0. This is 1. This has to be 0 because B is 0. This will be. Now I am going to combine this with A. Suppose I combine this with A or not A and B, then this would be 0, 1, 1, 1. Is that right? Which is same as A or B or A plus B. If you want to call it A plus B, no problem for me. So I can say this as, this is another simplification possible. By a similar logic you can prove, or you can also prove this by using some of the identities you learned earlier. Just showed you. Similarly prove that is what you think? A bar? Good. Why am I only choosing such of those things? Because every time you are knocking off a term. A simplification means reduction in the number of gates or reduction in the number of terms of a sum term, product term. Because the final expression is a sum of product expression. The sum of product expression There are two ways of reducing the logic. One is to reduce the number of terms. Number of product terms, if you reduce, you get a reduction. Or in each of the product terms, if you reduce the number of variables in that term, then also reduction. For example, a number product term is equivalent to an OR AND gate. There are 3 inputs. If there are 3 variables in the product term, I need a 3 input AND gate. Only 2 variables in the product term, I only need a 2 input AND gate. So you have to reduce in 2 ways. You have to reduce the number of product terms so that the number of inputs to the OR gate will be reduced. Because some terms feed to an OR gate. The sum of these product terms. That means each product term is fed into an OR gate. OR gate is equal to a sum. It's really OR operation. We call it sum just for sake of understanding. So how do you reduce the complexity of an OR gate, the number of inputs to the OR gate? By reducing the number of product terms, so that the total number of terms you need to sum or total number of terms for which you need to get an OR function is reduced. And each of these terms which are an AND gate output can be simplified by reducing the number of variables in that AND gate. So for example, if you take this logic function, I can reduce this by 2 ways. There are a total of 1, 2, 3, 4, 5 terms. Any number less than 5 is a reduction, and any number less than 3 in each of the product terms is also a reduction. So finally we got this function, isn't it? This is what we started with. I have to show you using the Boolean algebra. We have now developed that this is same as this. We will do it in a minute. So I am reducing it 2 ways. I am reducing the number of terms from 5 to 2, and each of these terms from 3 variables to only 1 variable in one case and 2 variables in another case. So 2-step reduction or 2-way reduction. That is why I am giving you the identities that are only relevant from that point of view. Boolean algebra, as I said, can be rigorously taught as a tool of simplification of Boolean functions. But at the practical level, we are looking at reduction of the hardware, both in terms of number of gates and number of inputs to each gate. That can be, so all the identities are relevant in that context. Namely, this is this, 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 and this. All of them are knocking off either a term altogether. In this case, I am knocking off a term altogether, or in this case I am knocking off a variable and a term. I am knocking off a variable in a term. So I have given you identities which will knock off an entire term or knock off a variable in a given term. Okay, do you understand this concept of Boolean algebra from the reduction point of view, which is our primary goal in this course? Digital design, efficient digital design. What is the parameter? The mantra: reduce hardware, increase reduction of hardware, cost saving, power saving, reliability increases, so forth, size increases, decreases, and so forth, so forth, so forth. So you keep that as a single point goal. From that angle, if you look at, we are going in the right direction. Now to quickly tell you that this is same as this, we will do a quick analysis of this. This is the original function, the canonical sum of product, written directly from the truth table, reading off the entries of the truth table for which the output is true. And I want to make it f is equal to a plus b. That is the sum of products. This is canonical sum of product. Any term of this type is called a sum of products because it is sum of product terms. And if it is minimum beyond which you cannot go, then it is also called a minimum sum of products. So my goal is to make it the minimum sum of products. So this is canonical sum of product. By repeated application you get sum of products which are simpler than this, and finally you get a minimum sum of product beyond which you cannot reduce further. Okay. Now, how do you do this? For example, can I use this formula A B bar, C bar and C, supposing I leave this term as it is for a minute. Right? C plus C bar is what? 1. Similarly, right? So I am combining these two terms and combining these two terms. So knock off this C plus C bar is 1. Knock off this C plus C bar is 1. So this becomes huh? Okay, thank you. Thank you. There you go. Now again I am going to use the same okay. Now this has to be reduced to this. You can use one of these identities here. A and A bar and B. I have an identity here. I have a variable and another term in which the variable is complemented and some other term. So if we treat this B C bar as another variable, A appears as A bar here. So when you have a variable and the same variable repeated in a complement form along with another variable or another variable along with other variables, this extra variable can be knocked off. Is that what it is? Is that not what it is? A or A bar B is A or B. That means the A bar gets reduced. Here also the A bar will get reduced. So the same as if you are not convinced, there are other methods of doing it. See, after all, as I said, you can several ways in which you can do it. You have to remember that is the problem with the Boolean algebra. You have to remember it has to strike you to apply the right identity to the right place, and you never know whether it can be simplified any further. Nobody is going to tell you this is the simplest. In exams, of course, they will tell you prove that LHS is equal to RHS. That is also a trick. There is also a trap there. You somehow start with LHS, go halfway, start with RHS, go halfway, and somehow make a big confusion, make so many terms and strike them off, remove them, erase them, strike them and say, therefore LHS is equal to RHS. So I don't know, but that is one way of looking at it. But in a rigorous way, if you are it's a question of whether you are going to try to do it for marks or is trying to do for a design, for living. Going to do a design for living and make a very efficient circuit, then you will not do all those dirty tricks, right? Then you have to make sure that you got a very simple circuit, the simplest possible circuit. So if you don't like this application here because it may not strike you here, what I can do is I can always combine this I am going to add one term here. I am going to reuse this term. I have already used this term A B bar C here and simplified here. I am going to reuse this term here, the third term A B bar C. I am going to reuse it. Now if I reuse it, I am going to combine these two. A I will leave this, and these two I will combine as It's also true. I have not done anything different. See, this one you understood. Oh, I should have combined the fourth term. Right. Okay, sir. Thank you very much. Okay, I should not have combined this term. You are right. I should have combined the fourth term, which have already been combined once. Fourth term has already been combined once. A, B, C, C bar, A, B, C. I am reusing this fourth term. So it becomes A, B, C bar. And take B, C bar out and write it as A plus A bar and knock it off and make it 1. Is it valid? Is it legal? Yes, it is. Because what is A or A? I can have an OR gate with the same input tied to all the inputs, still the output is A. A or A is A. What is A and A? Huh? A. This is saying if I have an OR gate, if A is 1, both the inputs are 1, the output is 1. If A is 0, both the inputs are 0, the output is 0. Similarly, in an AND gate, if A is 0, this is also 0, this is 0, this is 1, this is 1, this is also 1. So that means I can use repeatedly the same term again and again for simplification purposes. That is another way of doing it. So I had two methods here. At this time, I had this. Of course, all this time I knew that there is a simpler function which is A or B, C bar. A or B and C bar. Since I knew that, I was going to try. Supposing I give you this problem in the exam, up to this you may probably do by combining the A plus A bar stuff. First step, clear. Here, this is where the Boolean algebra's problem comes in from the practical point of view. So you may stop here and say, you will argue with me that after all I got this far, you have to give me full marks. Somebody will say reduce 1 mark and all. This is not a question of mark, as I said again. So problem solving for problem solving sake or problem solving for practical use. So here it is difficult for you to strike that it can be reduced further by looking at this as an identity corresponding to this, or if you don't strike this, if it doesn't strike this to you, this doesn't strike you, then you have to write it this way. But what if you don't? That's okay. What I am saying is, this way you are not sure of simplified process. Because now I had a goal, I want to show it to you that it's possible, I try to put it this way. It is possible that if I didn't give you the f is equal to A plus B C bar, is the output of this the minimum possible sum, you would probably stop here. That's okay, there's nothing wrong, I am just saying. So Boolean algebra tool is useful, but you will have to be careful. You should remember to apply correct identity in the correct place and be sure when to stop, beyond which you cannot reduce further. But we proved that it is possible now. This is Boolean algebra tool. Now again, this is a minimum sum of products. From canonical sum of products we came to sum of products. Any of these expressions in between is a sum of products, not canonical, not minimum. It is not the original line, it is not the final line. It is not sum of products because this looks like a product terms summed into a series. Finally you have this is the minimum sum of product. And each of these terms for which the output is true from a truth table is called a minterm. And there are 8 minterms, out of which 5 minterms have output true, 3 minterms have output false. So we talk about truth table, canonical sum of products, minterms, sum of products and minimum sum of products. Now an equivalent approach can be done from a slightly different angle. That's called De Morgan's theorem. Again, this is something which you might have learned even in high school, I suppose, in your set theory, if you remember. Do you remember set theory? Some of these things you learned in set theory. Well, quickly states De Morgan's theorem. And it can also be done in a slightly different way using De Morgan's theorem. Suppose I have an AND function and complement the overall instead of complementing each term, the same as I convert each variable into its complement and convert the operand into its operation into its complement. OR is considered a complement operation, and so AND operation convert into OR, A convert into A bar, B convert into B bar. So if you have a function A and B, the complement of that function can be written as OR operation of complement of A and complement of B. This we already proved in our slightly somewhat when I tried to get this NAND gate concept. Remember what is A and B? This is only a NAND operation. Did we not say this is same as inverting the inputs and ORing them? So not. Likewise, I can start with an OR operation and complement the whole way. Write it as OR complement as operation as complement as AND operation, A complemented as A bar, B complemented as B bar. Again saying the same way that I can have a NOR gate function. This is equivalent to complementing A and complementing B and feeding through an AND gate. These two identities are called De Morgan's theorem. De Morgan's identities or theorems. Theorem. De Morgan's theorem. Many times the De Morgan's theorem is used. So if you are not clear about that f is equal to A plus B bars, B C bar, that is for original function we talked about, you are only given the truth table. You are only given the min terms for which the output was true, 5 min terms for which the output is true. The original truth table or the canonical product, sum of product expression in terms of min terms. There are another way of approaching, because there are 5 terms for which the output is true. I want to simplify it to minimum number. Can I see which are the terms for which the output is not true? Output is false. Only 3 of them. Out of the 8 possibilities, for 5 terms it was true, if 3 terms it was not true. So is it possible probably to start with those 3 terms and simplify it, maybe instead of simplifying some 5 terms into a smaller number? Maybe it is possible, perhaps it is possible to start with 3 terms and simplify it. This approach can be tried. So the same truth table if you take, f is not true for the 3 possibilities. If you remember the original truth table, I will not write it now again. For the first row, for the second row and for the 4th row, output is false, isn't it? Is that right? The original truth table, row 1, row 2 and row 4. So what is it for row 1? A bar, B bar, C bar, for which the output was false. So f is not true for this combination, not true for this combination, and not true for is that right? These are 3 combinations where the output is not true. Now I am going to apply my De Morgan's theorem on that. We said if I have a function whose its complement can be obtained by applying De Morgan's theorem on each of the terms on the right hand side, So from here, applying De Morgan's, F can be written as which is same as this operation becomes AND operation, this operation becomes AND operation, and this becomes, each of these AND operation becomes OR operations, each of these AND becomes OR, and each of these variables gets complemented. That means it becomes A, R, B, R, C, this and complement removed, complement removed, complement removed. Correct? And this AND becomes, this OR becomes AND. This C becomes complement, D gets complemented, complement of B and complement of A get removed. And finally, C bar. So that means it is the same as I will rewrite it here to avoid confusion. This is, each of these terms is called a product sum term, because it is a sum operation, and this is called a sum of product of sum, product of sums. So this is a product of sum. F is POS, product of sums. Each of this is a product term, sum term. Multiplication of these sum terms gives the final expression. So it's a product of sums, and is also called max terms. Max term is what you got directly from the truth table. Min term, when you look at the ABC type of thing. Max term, when you look at it, is A or B or C. So OR operation, if you apply, it's called max term. AND operation. So max term of all the terms of the truth table, 8 terms of the truth table, each of them can be written as a max term. For some of the max terms, the output is true. Some of the max terms, the output is false. And the product of some expression is written using the max terms for which the output is false. Isn't it? Max terms for which the output is false, you write them, get a product of some expression. This is also called a canonical product of some expression, because canonical product of sum. So I can simplify this further by a repeated application of Boolean algebra to give me the minimum product of sum, minimum POS, like minimum product, sum of product. So I can start with the truth table, proceed with min term, canonical sum of products, reduce it to a minimum sum of products. Or I can give in a truth table, I can start with max terms, product terms, write a canonical product term expression for the output and reduce it further to get a minimum product of some expression. And if you do that by just multiplying this and applying repeated application of Boolean algebra, you will get that expression as, I will give you the result. I wanted to try it as a homework. F becomes A or B I want it in this form. I can always apply Boolean algebra. I said F is equal to A plus B C bar. Don't proceed from here and prove this, okay? I wanted to go through this exercise of taking the canonical product of some expression from the truth table which is true from, because I started with something which is true. Instead of starting something which is true, I started with something which is false. Apply De Morgan, that means this becomes something for which is true. So this is the function. But the expression is not sum of product, it is a product of some expression. I wanted to apply the product of some, to this product of some expression, our Boolean identities, known Boolean identities or unknown Boolean identities, any identity which I would have missed here is also fine with me, and get it in a minimum product of sum, and that happens to be this form. In this form I want. So can you do that as an exercise? That is ARB and ARC bar. So now I gave you a flavor because I didn't want to spend too much time on this Boolean algebra. But at the same time you should know it's a very powerful tool. Use very easy really. What is the big deal about it? Knocking off the variable wherever possible to reduce the complexity. It can knock off terms to reduce the input to the OR gate, knock off variables to reduce the input to the AND gate. That is the crux of the Boolean algebra. We did that. It is not all that complicated. The only thing is uncertainty. The right identity you should use. If it doesn't strike, what happens? And you never know when to stop unless you are given what is the minimum sum. Because you are the designer, nobody is going to tell you this is the minimum. If it is an exam, I can tell you reduce it to this form. If it doesn't come to that form, you know you have not got the result. So, but for that it is a good tool, but as I said, we will remove the uncertainty by applying the graphical method, the map method, which we will see in the next lecture.